Alright, welcome to my final video on integration by partial fractions. After that well-deserved break, we're on to a final exercise, which is going to be way less hard than the previous one, trust me. To be honest, I don't expect you to have an exercise that complicated in a traditional Cop 2 test. I was just about showing you how hardcore it could get, and if you can master that, you'll be so good at the exercises you'll see in your tests. This one's going to be special because there's two little details I don't want you to miss that are important. One of them is going to be about long division, and the other one's going to be a little detail of partial fraction expansions. So stay tuned for these two details, and let's get started. So this integral, the first thing I ask myself as always is, can I solve this using U sub or direct integration? Well, obviously not direct. With U sub, if I do it in my mind, I can notice that I'm going to have problems too. So obviously, since this is a rational function, the next question would be, can I expand this into smaller fractions to simplify the process? And that's what we're going to try here. For the first step, we ask ourselves, is this a proper or improper fraction? We can see that in this case, it is improper because this one's higher. Therefore, we need to apply either long division or synthetic division. So this is the first important detail in this video. What I'm going to do is I'm going to apply long division just to review that for you guys. If you're interested in synthetic division, just let me know in the comments. But in my case, I've always preferred long division, even though it takes longer. So going back all the way back to school, the way they taught me this is that this was some sort of person on top of a horse, and they were heading their way back home. And once they reach home, there's this house that they have, and the person belongs inside the house. So we'll put that over there. And the horse unfortunately has to go outside the house. So this is how that goes. And then we need to perform division. It's just like ordinary division, but with variables. So it's not that big of a deal. Notice that if I multiply everything by x, I get x to the fourth minus 3x cubed, and I always have to subtract this, right? So I'm going to put a parentheses just to avoid confusion. There's a minus always, and notice that if I distribute it, then the x to the fourths will cancel. That's great. I'll be left up with minus 2x cubed, and now I can lower the plus 6x squared, or I can lower the entire thing. It's pretty much identical. I'm just going to do that, and if I multiply everything once again by minus 2 this time around, and then I apply the minus, I'm not going to write that, but you'll be left off with just minus 18 because this and this will cancel out. Verify that for yourself. And now you have our new integral. This top part goes first, and then plus our new proper fraction, which is going to have our residue on the top, minus 18, over our original denominator, of course. So this is like, for the next day, we've got the same horse, but with only one person, and previously we had like a lot of people, or very heavy people. Now there's only one person, and the horse is happy, everyone's happy, we're happy because we can proceed solving the exercise. So I ask myself once again, U sub or direct? I can solve this very easily using just the power rule. But this, I'm still having a little bit of problems. Let's continue with the fraction expansion to see what happens. So I'm going to forget about the negative for now. And I go to step 2 on partial fraction expansion, which is about factoring the denominator. In this case, I can factor out an x squared. So x squared times x minus 3. And here's where the second important detail of this video lies. Take a look at this term, x squared. It seems like we have a quadratic term, an irreducible quadratic, but in reality, it's just a linear term repeated twice. So in terms of partial fraction expansion, instead of writing something like ax plus b over x squared, what we need to do is just be aware that this is just a linear term that's being repeated twice, and therefore we just have to put a over x and then another, like something like a b over x squared. Okay, so that's the proper way to do it. Make sure you really understand this and avoid that confusion. Then we just have a c over x minus 3 because x minus 3 is also a linear term. So on the left hand side I have 18, and I'm just going to not write the denominators because I know that they'll cancel out. And on the right hand side, instead of applying smiley face twice, I'm just going to do this quickly. So the way to do this quickly is to write a times the denominators for b and c. Forget that the one in the a. So times x squared times x minus 3. And plus b, do the same thing. So the denominators from a and c. And then plus c times denominators from a and b. So x times x squared. I'm going to leave it like that because notice that I can factor out an x from here, which gets rid of this. 1x over here, 1x over here. If you take a look at this denominator, it matches because then there's an extra x when you compare it to this one or this one, and therefore you need to factor out that x in the numerator to cancel it out with the one in the denominator so that both denominators can cancel, which is what we wish. So I'm going to rewrite this on the bottom here. 18 equals just ax times x minus 3 plus b times x minus 3 plus cx squared. And I'm going to solve this very easily just by setting two specific x values. So when x equals 3, I get rid of both a and b, and I can find out what c is. In this case, we got a c equals 2. Make sure you verify all this. The second value is going to be x equals 0. When we do that, we get rid of both the a and the c, and we can find out what b is, which is very convenient. And substituting back the c and b values into the equation, I get that a has to be minus 2. So now that I have my three missing variables, I can go ahead and rewrite my integral once more. So going back here, it's going to be equal to the integral of x minus 2 minus, open parentheses, a, which is minus 2 over x, plus b, and b is minus 6 over x squared. C is positive, so plus 2 over x minus 3 dx. I ask myself once more, can I solve this directly or with u sub? Yeah, I can solve all of this directly, and technically this one requires u sub, but you can also do it directly as well, so you have a little bit of experience. The first thing would be to distribute the signs, so minus minus is a plus, minus minus is going to be a plus, minus plus is going to be a minus. And now integral of x, just by applying power rule, is going to be x squared over 2. Integral is minus 2 is just minus 2x. And now we have 2 over x, and that's going to be 2 times the natural log absolute value of x. And now for this one, we do have to raise the x squared on the top and then apply the power rule, but we can do that in a much quicker way. So the way I do this is there's always 3 steps. Step 1 is to lower the exponent by 1. So my new one's going to have an x to the first power. The second step would be to take that 1 and multiply it over here on the denominator. So we're good here. We don't have to write that down. And the third step would be to always flip the sign. Since we have a positive, this flips to a negative. So 6 over x would be, minus 6 over x would be our antiderivative. Look how easy that was. And then for the last one, we've got a minus 2 natural log absolute value x minus 3. And I did that directly because I know it's a linear term at the bottom. But technically we do have to use u sub, u equals x minus 3. You'll get the same thing. That's how we know what this is. And then the plus c, don't forget that. And we're done. Remember that for these two cases, you cannot remove the absolute value bars. So we're done. Alright, so hopefully you got something out of this. I hope you do well on your partial fractions during your exams. And you can go ahead and take another coffee break. It's well deserved. I'll see you in the next time. Take care.